Hello and welcome to this video on how to determine the number of factors in exploratory factor analysis. My name is Geiser, I'm an instructor with QuantFish. In this video I will discuss different ways to determine the number of factors in an exploratory factor analysis. That is usually one of the key goals when you run an EFA, to find out how many factors do you need to explain the correlation structure of your observed variables, and how many factors are sufficient, and is this an interpretable solution where each factor has a clear meaning and interpretation. So let's get started. The first thing that I will talk about are criteria for factor selection that are based on the eigenvalues of the correlation matrix. Second, I will talk about model fit statistics, and then third and lastly I will talk about criteria related to the interpretation of the factors, which is usually done based on the factor loading patterns. So let's get started with the eigenvalue criteria. The eigenvalues are an indication of the importance of a factor, or a measure of how much variance is explained by a factor, and so therefore the greater the eigenvalue, the greater supposedly the value of a given factor or the explanatory power. And so one very simple criterion for factor selection rests on the size of the eigenvalues, and that's the so-called Geiser criterion, according to which all factors with an eigenvalue greater than 1 should be retained. So that's a very simple criterion. All you need to do is look at the eigenvalues, which are usually provided by programs for exploratory factor analysis such as SPSS, and or take a look at a plot of the eigenvalues like I did here, where you can see in this scenario here we had 7 factors that were extracted, and the first factor here, only the first factor has an eigenvalue above 1. All the other factors fall below that threshold, so according to the Geiser criterion we would retain only one factor, no more than 1. Now the Geiser criterion is appealing because it's very simple. However, it usually does not lead to a meaningful factor solution. Usually with that criterion we end up with a number of factors that is either too small or too large. Now there are better criteria related to the eigenvalues, and the one that is a little bit better than the Geiser criterion is the so-called Scree test. Now I put test here in quotation marks because this is not really a test. So in terms of a statistical test where you reject a null hypothesis or you retain a null hypothesis or something like that, it's much more subjective than that, but it's often called a Scree test in the literature. Now what does the Scree test do? The Scree test again looks at the eigenvalues in a plot that is also often referred to as a Scree plot, and then looks at a characteristic point where the curve of the eigenvalues flattens out. So Scree is, so say in a mountainous region, are the rocks that assemble at the bottom of a big mountain where they fall down, and then at some point the slope becomes so flat that the Scree will not roll down further the mountainside, and so it'll stay there. And so the Scree would stay about here if it fell down from the mountain, because here it becomes sufficiently flat. So we're looking for a characteristic point where the whole curve flattens out, and as you can imagine that is fairly subjective, and oftentimes it's not very clear in the distribution of the eigenvalues where this point should be, and then also should it be above that point, or should you retain all the factors above that point, or one more. So it's not 100% clear. However, the Scree test tends to be a little bit better in terms of retaining a meaningful number of factors than the Geiser criterion, so it's somewhat of an improvement, and it certainly doesn't hurt to take a look at the Scree plot, because it tells you at least whether there's one strong G factor as opposed to a lot of other factors, like in this case where clearly there's only one factor that is very strong and then the remaining factors are much weaker. So that can be important information for you to know, because it it indicates that the variables are all highly correlated. So there is a strong underlying common ability or common factor or trait here, even though more than one factor may still be needed to properly account for the correlation structure. So this does not mean that really you have to have only one factor, as we will see. Now, there's a third criterion that is related to the eigenvalues that is actually a really good criterion, useful criterion for factor selection, and that's called parallel analysis. Now, parallel analysis not only looks at the eigenvalues of the data, the actual data, like we already did, but it also looks at simulated data. And then it compares the scree plots or the eigenvalue plots of the real data to the plot that is obtained for random data that is simulated, as you can see here. So here you can see we have the same data scree plot that we previously looked at, and in addition to that we also have a scree plot for data simulations. Simulations here meaning there was a generation of random variables that should not be correlated beyond chance. And then those also produce eigenvalues, because there are some chance correlations. When you simulate random data due to sampling fluctuations, not all of the correlations in the simulations will be exactly zero, and as a result you will also get eigenvalues, and you may even get eigenvalues greater than 1. You can see there's 1 here in the simulated data that is at least 1, I would think, so, or very close to 1. And so then we compare those eigenvalues for the random data to the actual data. And computer programs such as JASP, for example, will do that for you, and they'll run many simulations, so not just one simulation, but they'll average those across multiple simulations, those eigenvalues, and then they will give you the plot of the simulated eigenvalues in the same graph so that you can compare them. And then what we can take a look at is where those two graphs intersect. So at which point does the scree plot for the simulated data intersect with the scree plot for the actual data? And then we would say we should retain as many factors as appear before that intersection. So in this case 2. So you can see here that those are close, the eigenvalues for the second factor, but the one for the simulated data is still lower. And so then after that we have the intersection here of the two curves. So in this case we would say it's reasonable to extract 2 factors. And it turns out this is also a more meaningful solution substantively than a single factor solution in this example. We'll see that later. So parallel analysis is really the best of the eigenvalue related criteria. So if you have a choice between the Geiser criterion, the scree test, and parallel analysis, use the parallel analysis. The parallel analysis performs best in terms of retaining the correct number of factors, as has been shown by simulation studies where we know the true number of factors, and then we can see which criterion leads to the solution that we know is the true solution, and parallel analysis in simulations has performed better than the other criteria. Now, other than eigenvalue criteria, we also have fit statistics, and most notably when we run maximum likelihood factor analysis, which is one recommended type of factor analysis, then we can obtain a chi-square test of model fit, which is a statistically harder criterion than the previous ones that we have looked at so far. So with a chi-square test, we can actually test a null hypothesis. And here the null hypothesis is that the observed correlation structure in our data is equal to the correlation structure that is implied by our factor model. For example, the one implied by a single factor model, or the correlation structure implied by a two-factor model. And that null hypothesis can then be tested with a chi-square test, which is a statistically hard significance test that allows us to obtain a p-value for testing that null hypothesis. The alternative hypothesis here is that the observed correlation structure is not equal to the model implied correlation structure, meaning under the alternative hypothesis H1, our model would be rejected or would not fit. So if we have to reject the null hypothesis, then that means the model is rejected. I can show you an example here. The first one is for a one-factor model or single-factor model that I fit to the eigenvalues that we saw previously, or to those data. And you can see I obtained a chi-square value with 14 degrees of freedom of 54.73 with a p-value that is smaller than 0.001, which means the null hypothesis that a single factor model generated the correlations in our data was rejected here. So a single factor model does not fit the data because this p-value is smaller than a commonly set alpha level of 0.05, and therefore the null hypothesis can be rejected. Now, what about a two-factor solution? For a two-factor solution for the same correlations, I obtained a chi-square value with 8 degrees of freedom. You can see we have fewer degrees of freedom for two factors because the model is less parsimonious. We have more parameters to estimate, more factor loadings. And so the chi-square then is also markedly lower, 14.09, and the p-value is 0.08, which is greater than an alpha level of 0.05, meaning the null hypothesis that a two-factor model fits the data does not have to be rejected. So a two-factor model, according to the chi-square test of model fit, can be retained. It's not falsified based on the chi-square test, so we may accept that model, at least unless we have other criteria that speak against a two-factor solution here. Other than the chi-square test of model fit, there are also other fit indices or fit statistics, and the reason for that is that the chi-square test of model fit can be very sensitive to a model misspecification, even minor misspecification or misfit when you have a large sample size, and also under maximum likelihood estimation when you have non-normal data, the chi-square test can be, or the chi-square statistic can be inflated. And therefore, other fit statistics have also been developed for model evaluation. I will show you some of the common ones here that programs for EFA output, or some programs at least, when you run a maximum likelihood factor analysis. One is the root mean square error of approximation, RMSEA. Here, a good model would show an RMSEA value below 0.05. Also, there is an index called the comparative fit index, CFI, and the Tucker-Lewis index, TLI, that compare the target factor model to an independence model where the covariances are all 0 in the population. And so those are incremental fit statistics that show us how much better a factor model is than no model at all. And so here, when we find values close to 1, specifically greater than 0.95, we think of a model as being a good fit. And then finally, we also have descriptive fit indices that fall into the category of information criteria, such as ACAG's information criterion and the Bayesian information criterion, BIC, where we can compare, for example, a one-factor model to a two-factor model, and then we would prefer the one that shows the smaller value of, for example, BIC. Let me show you that also in the example. Here I have a table with a fit statistic summary for the one-factor model in the second column and the two-factor model in the third column. The chi-square values we already discussed. According to the chi-square, only the two-factor model fit the data. The root mean square error of approximation looks better for two factors also and is below the recommended threshold of 0.05 for two factors, whereas it is above the threshold for a one-factor model. So the RMSEA would also favor a two-factor solution. The Tucker-Lewis index, which I picked here in this case, TLI, was 0.95 for a one-factor model and 0.99 for a two-factor model. So meaning also it was better in terms of the 0.95 threshold for two factors, and it was a little below that for a single factor model. And then finally, the Bayesian information criterion was smaller also for two factors with a value of -3.4 as opposed to -29 for a one-factor model. So all the fit statistics in this case would speak for a two-factor solution as opposed to a one-factor solution in the same way as parallel analysis indicated. Finally, what we should also do always is we should look at the loading pattern of a given solution and whether it's interpretable. So there's no point in accepting a two-factor solution if the loading pattern is meaningless and if one of the factors has no meaningful interpretation or no substantial loading. So that's also always important, specifically looking at the rotated factor loading matrix. So rotating the factors usually improves the interpretation, specifically oblique rotation, so meaning where the factors are allowed to correlate, usually leads to better simple structure, better interpretability of the factor loadings. And that's what I did here. I used Promax rotation with maximum likelihood factor analysis of my two-factor solution in SPSS. And you can see the first factor clearly loads all the math test variables in my example here. So those have substantial loadings, whereas all those variables have negligible near zero loadings on the second factor. And then the KFT test scores, which are from a German cognitive abilities test, all load on the second factor with a slight ambivalence or ambiguity of the last one. The quantitative subscale also has a pretty substantial cross-loading on the first factor. You can see here this is 0.246 versus 0.486, but it does make sense because the first factor is a math factor which uses numerical material also, and that's, so say then kind of makes sense that the quantitative numerical subscale of that cognitive ability test has somewhat of a cross-loading on the first factor as well. So in summary, the two-factor solution not only fits well according to most criteria, but also looks good in terms of the loading pattern and interpretation. Those two factors have a clear interpretation. There's a clear simple structure of the factors where most variables load highly on only one factor, not both, so that both of them can be clearly interpreted. The first factor as a math factor and the second factor as a cognitive abilities factor. I hope you found this video useful to learn more about factor selection criteria in exploratory factor analysis. Check out the description for additional resources, including workshops that we offer through QuantFish on factor analysis and other topics. And I'll see you next time.